Dear students, welcome to the last lecture for this semester. Today we will talk about visual analytics methods for creating and validating regression models. At the beginning, I will give a short motivation why regression is a suitable and powerful method. Afterwards, we will have a look on some examples where regression was used for data analysis. Then I will talk about different regression methods in more detail, comprising automatic, interactive, and partition-based regression methods. Another important aspect is the validation of regression models. So we will discuss how the validation of regression models works. And finally, I will show you two use cases where regression methods were used. So the first use case deals with the prediction of gas consumption, while the second case is a medical scenario where regression was used to search for breast cancer risks. So why we deal with regression in visual analytics? Regression is a core part of statistics. With nowadays big data, manual evaluation of relations is no longer feasible. There are automatic regression models, which however exhibited a number of limitations and drawbacks. On the other hand, there are interactive regression models using visualizations of the effects of modeling decisions have a great potential for complex modeling tasks in engineering, climate research, or medicine. So there are a lot of successful case studies in the visual analytics community. Let's have a look on some regression examples. Once we have acquired the data with multiple variables, only very important question is how the variables are related. For example, we could ask for the relationship between people's weight and height, or study time and test scores, or two animal populations. So regression is a set of techniques for estimating relationships, and we will focus on them in this lecture. A linear relationship is one of the most simplest types of relationships. So the process of finding a linear relationship is called linear regression, and this has many applications. For example, we can relate the force for stretching a spring and the distance that the spring stretches called Hooke's law, as you can see in the left diagram, or explain how many transistors the semiconductor industry can pack into a circuit over time called Moore's law, as you can see in the right diagram. Thus, our goal is to find the function which best fits the points in the diagram. And in these examples, the points can be approximated by a linear function. In the lecture about linear dimension reduction, we already talked about the PCA, which is one of the most commonly used linear dimension reduction methods. The question is now how linear regression and PCA are related to each other. In 2D, we search for a 1D representation as a regression line, or a 1D vector to represent the two-dimensional data best. So we minimize the distance between the 2D points and the line in the least square sense. The specific error measure is different. So in linear regression, the error squares are minimized in the y direction. With PCA, the error squares are minimized perpendicular to the straight line, so it's an orthogonal regression. Let's have a look on another example where regression methods can be used to predict the values. Assume a gas provider needs accurate predictions of future gas consumption, for example, to decide on the use of renewable energy. So the gas provider has collected data relating to the temperature, wind speed, and direction that may be combined with day of the week, month, or season to compute a regression model. To keep things simple, we want to use a linear regression model to predict future gas consumption. This means we search for variables that significantly influence our target. So this would be in this case gas consumption and their weight. We also want to know how reliable our model is in terms of how accurately can we predict the gas consumption based on a weather forecast with a certain reliability. So instead of just use a single scalar value, we have a vector x1 to xp for every data point. So we have n data points, just like before, each with p different predictor variables or features. We will then try to predict y for each data point as a linear function of the different x variables, which is called multiple linear regression. So in this example, gas consumption is predicted based on temperature and time of the day. The resulting curved surface, which is the model, is compared then to the actual data. Another example deals with the life expectancy in Germany, which differs up to 6.3 years for males between Munich and Tübingen, compared to Demmin and Bürdigreis, where the life expectancy differs up to 3.5 years for females. Here, different data aspects were collected, comprising data related to income, education and status, unemployment, gross domestic product, air pollution, crime rates, lifestyle including smoking, alcohol consumption and physical activity, as well as healthcare related data including the density of stroke units and specialized treatment for cardiac diseases, as well as climate related data. The questions we are interested in are then, can we explain the difference in life expectancy? Are there factors involved that may be changed? And can we predict the amount of improved life expectancy in case certain measures are taken? We will see throughout this lecture whether we can answer these questions. Regression analysis serves to estimate such relationships. So it has two major categories of application. The first one are predict values of the dependent variable given the input parameters. For example, gas consumption or support for decisions in marketing. The second application is explain how the independent variables influence the dependent target variable. Because independent variables are, for example, health measured as life expectancy. So the goal is to quantify the strength of the relationship. For the life expectancy example, the strongest positive influence have income per taxpayer, disposable income, caregivers in the home, and the strongest negative influence have unemployment rate and not having a high school diploma. Here we see another regression example where mortality, meaning how many persons died within a year, was plotted against the income. We can see that there exists a negative, highly significant correlation between both quantities. This means mortality is higher among people with lower incomes, and there may be many reasons for this, such as poorer medical care or low quality food. Another important aspect is the relation between correlation and causal effects. A verified and strong correlation may be related to a causal effect, but often this is not the case. Is a low educational level the cause for later health problems or consequences of already existing health problems? So homeless people are in bad health. Did they get homeless because of bad health, or is bad health the consequence of being homeless? So there's a strong significant effect that people with larger shoe sizes die earlier. Is shoe size the true reason? Thus, an expert is needed to interpret results of regression modeling. Often further hypothesis-driven research is necessary to investigate the results of exploratory regression modeling. Here you can see 4 different types of causality. So the causal link describes the phenomena that even if there is a causal link between x and y, correlation alone cannot tell us whether y causes x or x causes y. The second type is a hidden cause, thus a hidden variable z Thus, a hidden variable z causes both x and y, creating the correlation. The third type is the confounding factor. Here, a hidden variable z and x both affect y. So the results also depend on the z variable. The last type is named coincidence, which describes a situation where the correlation just happened by chance. This means there are different reasons for a correlation. For example, the shoe size phenomenon is based on a hidden cause, the gender difference in mortality, for example. There are different regression models that we will discuss in this lecture. So we will start with a simple linear model comprising 2 variables that influence the target variable. Then I will explain partial linear regression models, which is a form of semi-parametric model, since it contains parametric and non-parametric elements. I will then continue with piecewise linear regression models, which is a form of regression that allows multiple linear methods to be fitted to the data for different ranges of target variable. After linear models, we will see nonlinear regression models, which are typically quadratic or cubic to model the more complex relations. Finally, I will introduce the logistic regression models, which is a statistical model that in its basic form uses a logistic function to model a binary dependent variable. Before we start fitting a regression model, we need to take a closer look at the data, because regression modeling is sensitive to the data quality. To receive reliable regression outputs, it may be necessary to select a subset of items with more reliable data, remove outliers because outliers statistically can influence the regression model, and investigate imputation strategies for missing values to improve the quality of the results. Moreover, before we start with a closer look at different regression methods, we need to clarify some terminology. Assume we are going to fit a line which is given by this formula. Here, y is called the dependent, response or regress variable, and the xe are called the regressor, explanatory, predictor or independent variables. The bi are called regression coefficients. They are the weights of the independent variables. A value very close to 0 indicates little to no relationship with the dependent variable, and large positive or negative values indicate large positive or negative relationships, respectively. The epsilon is called an error term or noise, which represents the fact that our data won't fit the model perfectly. Besides the usual function term, the model can also be expressed in a vector notation where B contains all the BI values as column vector and large X all dependent variables as a row vector. In this lecture we restrict to one target, so multiple targets multiple target variables is not considered in this lecture. To determine the regression coefficients, we have to make spatial assumptions. For example, we assume that our data can be described by a linear model. The specific parameters are determined based on a certain norm that serves to provide the best fit. Most frequently, the sum of the square differences is minimized, which is called the least squares fit. An alternative to that is the least absolute deviation. So to increase the quality of the fit data should be evenly spread on both sides of the regression line or the regression curve. To validate the goodness of the fit, we determine the correlation coefficient, which ranges from -1 to 1, where the R² value is always positive and indicates the variability explained with the model. So here you can see the formula of the R² value, or of the R value, which can then be squared. So the square of the correlation coefficient, these R² values, will then be always positive and is called the coefficient of the determination, and this is also equal to the proportion of the total variability that is explained by the linear model. Another assumption we made to build the regression model is that the explanatory variables are independent. So the variables that are dependent on each other should be analyzed with care, or one of them should be removed. If some variables are perfectly correlated, the regression coefficients cannot be determined because there's no solution. As I mentioned before, the R² value is the most important quality criterion in this context. However, the coefficient of the determination increases with the inclusion of additional variables, and thus there's a risk of overfitting our model. And therefore the adjusted coefficient of determination is usually used for practical applications. In contrast to the unadjusted coefficients of the determination, the adjusted coefficients of the determination penalizes the inclusion of each newly added explanatory variable. Besides, also the archaic is also frequently used for quality validation. It incorporates a penalty for complex models with the same quality of a fit. A model with less regressors has a lower, or in this case a better arc value. Archaic prefers less complex models and is less prone to overfitting. So a modified version corrects, for example, the sample size. On the left side here, you see the result of a simple linear regression model with one independent variable. So the data was artificially generated with random noise added to a linear term. And based on the least squares optimization, the regression coefficients were determined. On the right side, you see a cubic regression model with confidence interval displayed here in red, and the model represented by the green line is applied to the test data and does not perfectly fit the truth indicated by the blue line. In conclusion, so we can summarize that polynomial regression is a powerful method. A polynomial up to a certain rank is determined to yield an optimal fit. However, polynomial regression may suffer from overfitting. So there is a risk of with increasing rank of the polynomial and small sample size to overfit our data. In the extremum, a polygon of a rank n is used to fit a sample of size n, and of course then the fit is perfect, but overfitting is extreme, so you can not apply this model to another dataset. Also, linear regression may be prone to overfitting when the sample size is small and too many regressors are used. As a rule of thumb, one can assume that for a sample size of 1000, no more than 4 regressors should be used. In addition, we want to talk about multicollinearity, which is a specific statistical phenomenon. So it means that some explanatory variables are not independent. And thus it is difficult to test how much the combination of the independent variables affects the dependent variable or outcome within the regression model. So in statistical terms, a multiple regression model where there is high multicollinearity will make it more difficult to estimate the relationship between each of the independent variables and the dependent variable. So small changes in the data used or in the structure of the model equation can produce large and erratic changes in the estimated coefficients on the independent variables. To ensure the model is properly specified and functioning correctly, there are tests that can be run for the multicollinearity. In most cases, again, the R-squared value is one of such measuring tools. When the correlation, so the R-squared value between two variables is larger than 0.8, possible collinearity exists. And if the R-squared value is larger than 0.95, it definitely occurs. Another diagnostic test is the variance influence factor. The variance influence factor measures how much the behavior, so the variance of an independent variable is influenced or inflated by its interaction or correlation with the other independent variables. So the variance inflation factors allow a quick measure of how much a variable is contributing to the standard error in the regression. So normal variance inflation factor values are smaller than 5. And if this value is larger than 5 or at least larger as 10, there identifies multicollinearity. In case of a pair of variables x1 and x2 being multicollinear, only one of them should be selected for the regression models, because otherwise our results are not high quality. Another important aspect in regression modeling is the scaling of the variables. So the variables may have very different units and scales. For example, studies related to criminality in the US involve the portion of young men. So in this example, aged between 18 and 24. Then the portion of non-white persons, average income, and population density. And for expressive regression models, the data needs to be scaled. A frequent type of scaling is to center the variables and normalize them with respect to the standard deviation sigma. So the current value of a variable is subtracted by the mean value, and this result is divided by the corresponding standard deviation. This normalization leads to a new scale with mean is 0 and standard deviation is 1. As I mentioned in the introduction, there are automatic methods to build a regression model. So automatic techniques search for first dependent variable that has a high explanatory power for the target and compute the regression coefficients. Then iteratively further dependent variables are added until the quality of the fit does no longer increase significantly. The most common algorithm in this field is the stepwise regression developed in the 16th. So in each step, a variable is considered for addition to our subtraction from the set of explanatory variables based on some a predefined criterion. And usually this takes the form of a sequence of f-tests or t-tests, but also other techniques are possible, such as the adjusted r-squared or archaic values. Regarding implementing such things, I can recommend to statistic packages such as R provide these automatic techniques. However, there is a problem with, of course, automatic methods, because in every step a numerical score is evaluated, and several variables may have almost equal scores. Thus, the decision is somewhat arbitrary. So the decision is one step may affect further steps. In general, automatically generated models are objective, may provide reasonable explanations for the dependency of the target variable from the dependent variables. However, there are also some drawbacks compared to other machine learning methods, such as decision trees. So first, automatic methods do not integrate user input, and thus the results may be partially not interesting or do not consider essential aspects such as partitions in the data that are less reliable. Special effects such as the Arabic oil embargo in the 1970s on economic factors are, for example, ignored. Another problem are existing outliers in the data. Since regression results strongly depend on outliers that are hard to determine automatically, the results may be misleading. Moreover, automatic regression models tend to be unnecessarily complex and may suffer from overfitting, as we've seen before. And due to these problems, we might have limited trust in the results. So instead of computer-assisted data analysis, where the user can influence the results, is probably more favorable. There are two types of points that need specific consideration. An outlier is any point that's far away from the rest of the data. So there are different definitions and ways of quantifying them depending on how you define far away. An influential point is a point for a statistical calculation whose deletion from the data set would noticeably change the result of the calculation. And in particular, in regression analysis, an influential point is one whose deletion has a large effect on the parameter estimates. Thus, an influential point is an outlier with high leverage that significantly affects the slope of a regression line. So one option to assess the individual points is to compute the leverage, which is a measure of how far away the independent variable values of an observation are from those of the outlier observations. Computing the leverage of individual points supports the decision to exclude such points from the model building, and the leverage hi for point I is between 0 and 1. So typical values depend on the sample size n and the number of variables in the regression model P. If hi is larger than 2p divided by n, the corresponding point should be checked. Outliers should be checked with respect to the influence on the regression slope, so they may or may not follow the trend. Outliers are often influential if they deviate strongly from the mean of the x values, and the computation of the leverage effect considers this. However, outliers are not necessarily wrong values. They may be caused by too low sampling. So increasing the sampling could avoid this outlier problem. The figure illustrates these concepts. So, since influential points can really mess up linear regression results, it's important to deal with them. So sometimes such points indicate the need for more data gathering. So if most of our data is concentrated in one area and our sampling methodology was flawed, we might have missed data points in the region between the main cluster and an outlier. And alternatively, if such points don't indicate a problem in the data collection, but really just are irrelevant outliers, we can remove such points from the analysis. An alternative is to take each point and fit the model with and without that point. So we can compare the two results. The more different they are, the more influential the point would be. The Cook's distance is a measure of how influential each point is that captures exactly this idea. So the definition is based on fitting the full model, which means using all of our data, and then fitting the model again, but this time excluding our point I. In general, robust regression analysis avoids the need for manual checking of outliers, and the basic goal is to replace the least squares optimization, where the penalty for outliers is very large. For this purpose, in most cases, the Residual approach is used. Here a subset of points is chosen and the model is computed, validated, and the error is recorded. Then try other subsets and validate again. You have to choose the best subset where probably the best subset has no or very few outliers. The problem is that RANSAC has many parameters that influence the results, and you have to decide which subsets are used, how they are chosen, and when to terminate the algorithm. To support the user in model building, various visualizations are developed in the past. So within the next slides, we will have a look on quantile plots, partial residual plots, partial regression plots, and partition-based visualization. And often, in addition, interactive regression model building reveals that derived quantities needs to be considered. For example, the horsepower against weight in cars to predict the oil consumption. Before we start with interactive regression model building, we have to pre-process our data. And an important step is to check the univariate distribution of the explanatory variables. So ideally they are symmetric, close to a Gaussian distribution, but if they're not, we have to check whether a log transformation, square root transformation, or multiplication of explanatory variables may improve the distribution. Sometimes it makes sense to replace the original data with transformed re-expressed data. So for example, the prediction of life expectancy revealed that logarithmic-sized air pollution parameters are essential parts of a regression model. So afterwards, check for outliers, whether they are influential, and finally standardize the explanatory variables with respect to the range of 0 to 1. Thus we can summarize that feature selection and transformation, as well as handling of outliers, are challenging tasks in model building. Here you see two examples for partial regression plots. So a partial regression plot attempts to show the effect of adding another variable to a model that already has one or more independent variables. It is also called added variable plot, which was introduced by Mosteller and Turkey in 1970. It enables us to visualize the regression coefficient of a new variable being considered to be included in a model, so the plot can be constructed for each predictor variable. Let us assume we want to test the effect of removing variables x from a model, and let the response variable of the model be y. First, we regress y on all variables other than x and store the residuals, which are called y residuals. Afterwards, we regress on x on all the other variables included in the model. So these are called then the x residuals. Afterwards, we construct a scatter plot of the y and x residuals. The question is now, what do the y and x residuals represent? So the y residuals represent the part of y not explained by all the variables other than x. And the x residuals represent the part of x not explained by other variables. So the slope of the line fitted to the points in the added variable plot is equal to the regression coefficient when y is regressed on all variables including x. A strong linear relationship in the added variable plot indicates the increased importance of the contribution of x to the model already containing the other predictors. Based on the partial regression plot outliers, we can identify the influence of the regression analysis. So here in this case, we can see that on the left side, two outliers heavily influence the regression analysis, and on the right side you see the partial regression plot of the SO2 versus the mortality, where the data was normalized for education, population density, rain level, and proportion of non-white persons. Another plot for the regression interpretation are residual plots. So a residual plot is a graph that shows the residuals on the vertical axis and independent variable of the horizontal axis. When the residuals with the residuals we can understand how much the prediction of y(e) depends on xi. Thus the residuals are the distances to the regression line. In this schematic, ye denotes the predicted value according to the model, or ye with the roof on it, and where ye represents the real value of y. So the residuals can be easily computed by subtracting both values. If the points in the residual plots are randomly dispersed around the horizontal axis, a linear regression model is appropriate for the data. Otherwise, a nonlinear model is more appropriate. Residual plots display the deviation of the data to the regression model, so the resulting variation not explained by the model. The distribution of the points should look like random noise. Otherwise, systematic error should be checked for, eventually leading to a refined regression model. For example, the left residual plot in the bottom row shows random noise, and the other three systematic errors of the regression model. We can summarize that residual plots indicate the overall quality of a model, and whenever there are striking nonlinearities. So residual plots do not reveal which explanatory variable causes the nonlinearity, and also outliers are hard to detect, and for this case partial residual plots serve better for this purpose. The next type of plot are partial residual plots. So when performing a linear regression with a single independent variable, a scatter plot of the response variable against the independent variables provide a good indication of the nature of the relationship. If there is more than one independent variable, things become more complicated. Although it can still be useful to generate scatter plots of the response variable against each of the independent variables, this does not take into account the effect of the other independent variables in the model. So assume we consider this multiple linear regression model with two independent variables. To generate a partial residual plot, we first regress y and x on z and compute the corresponding residuals. Then we regress y roof on z roof, and the resulting errors correspond to those of full regression. Partial residual plots, which we see on the next slide, serve to check for problems and outliers, as well as to identify influential points that need investigation. Thus, the model is verified and refined and can then be used to answer questions. Let's have a look on some examples. Consider the following data: gasoline demand, gas consumption, and income. And scatter plots for each independent variable with respect to the target variable do not indicate strong correlations. However, the multiple regression fits quite well. And computing the partial residual plots of the multiple linear regression indicate a good fit. However, partial residual plots do not take the variance of the remaining variables fully into account, so they underestimate the scatter of points around the line, where the amount of underestimation depends on the strength of the correlation among the independent variables. A comparison with partial regression plots show that nonlinear patterns are better detected in partial residual plots. However, residual plots better indicate how the target changes as a consequence of changes in the explanatory variable, since the original scale is maintained. Here you can see a visual comparison between a partial residual plot on the left side and the partial regression plot on the right side. So the 95% confidence ellipse illustrates the different amount of scatter. Note that the residual plot maintains the original scale, while the points in the regression plot are zero-centered. And we see on the right side that more outliers occur compared to the left side. In this example, you can see a visual comparison between a partial residual plot on the left and the partial regression plot for simulated regression with one quadratic component on the right side. And the left view indicates that the quadratic relation is better, while the right view shows many outliers. Another type of plots are quantile plots. So these are graphical methods for comparing two distributions by plotting their quantiles. They are used to find out whether two datasets come from populations with a common distribution. So a ggplot is a plot of the quantiles of the first dataset against the quantiles of the second dataset. If the two distributions are similar, the points in the ggplot are very close to the diagonal line where y is the same as x, where points are always non-decreasing on x. So the experts can compare the distributions according to the skewness, location, and scale, where ggplots serve these purposes better than histograms or raw distributions. Here you can see a comparison of a scatter plot and a ggplot. So to generate the ggplot, observed values of two characteristics whose distribution one wants to compare are ordered in each case according to the size. And these ordered data are combined to pairs of values and plotted in a coordinate system. If the points result in approximately a straight line, one can assume that the two characteristics are based on the same distribution. The procedure is problematic if there are different numbers of observations of the two characteristics, because this can be solved with interpolation methods to interpolate the missing values. An example is given here for approximately 110 warships of the outbreak of the Second World War. So the variables length and breadth were collected, and the scatter plot shows that there are obviously two distinct groups that stand out clearly as clusters. And for the GG diagram, the data were standardized to facilitate comparability. You can see from the gap in the dot plot the decomposition of the data into two clusters. And for the bottom left cluster, the type of distribution appears to be the same for both variables. And for the second cluster in the upper right, the width tends to be larger compared to the first cluster. So the bulk in the plots shows that here the distributions of length and width are unequal. ggplots can also be used to check the distribution of a variable. So the table shows values of an artificial data set comprising the variable data. And to generate the ggplot, we sort the data and standardize them. And this means we compute a zero means distribution. And afterwards, the z values are computed by dividing through the sample size S. The z values are transformed for quantile numbers. So, for example, 0.04 for x means that 4% of the values are below x. And perfectly correlated values would appear on the main diagonal in case the real data distribution corresponds to a normal distribution. In more complex scenarios, relations may be locally strongly different. Therefore, different models and assumptions are needed in different model parts to predict the data. The user's understanding which regions or subsets should be analyzed separately should be supported. An example for this is shown in the figure here. So in the left figure represents a global correlation which can be expressed by global regression models. The middle image shows a correlation that occurs only locally. Here a partition-based regression analysis is needed, whereas the right image shows no relevant correlation at all. What we want to have is a partitioning of xe and xy with respect to the target variable t. So a partition is represented as an interval in 1D and an axis-aligned rectangle in 2D. There are two ways how continuous variables can be partitioned. So in a domain uniform partition, each partition has the same size, and in a frequent-based partition, each partition has the same number of elements. The frequency-based partitioning has the advantage that all partitions have sufficient elements for identifying statistically significant regression models, and the partitioning may be performed automatically, for example with a determination criterion that relates to the minimum significance level. Finally, let's take a look at the concrete application examples where regression methods were used. Basically, some requirements can be defined which an visual analytics system for regression analysis should fulfill. So first, the system relate known results to regression models. Second, it should support the identification of subsets with a different behavior and should allow separate analysis of these subsets. Moreover, the users should be able to analyze the model behavior at selected points in the high-dimensional space. In addition, a visual comparison of different models and corresponding regression coefficients or archaic values should be supported to find a suitable model. Another important fact is the analysis of large datasets with many elements and variables and larger regression models. Besides, the validation of regression models with independent test data should be supported to assess the quality of the model. And last but not least, all actions should be performed in real time. Our first case study deals with the energy consumption. So the demand for natural gas is influenced by various factors, including temperature and potentially other weather factors, day of the week, and daily hours. And a precise understanding of the mutual influence of calendric and meteorologic aspects is essential to accurately predict gas consumption and thus to ensure supply and enable cost minimization. Partition-based visualization is used, which means continuous variables are binned to identify local correlations. And the influence of individual features and pairs of features on a target variable, so in this case the energy consumption, is displaced first, similar to the rank by feature framework, which does not support regression-based tasks. Here you can see plots that show the influence of single variables on the energy consumption. They are ranked by the R² value. So the temperature has the highest influence. This is reasonable because probably more energy is needed in wintertime. And similar aspect is encoded by the day of the year, where in summertime the energy consumption is lower than in the rest of the year. Besides single values, the influence of pairs of variables on energy consumption is depicted. So in this case, the color encodes the target, which is the average consumption. There are also use cases where both, so the target variable and the independent variable radiation, may be partitioned based on the domain or frequency, as you can see in the left image. However, when two independent variables are partitioned, one frequency-based and the other domain-based, the resulting visualizations are difficult to interpret, even for a domain expert, where in this case, color encodes the target variable. In the used regression framework, so regression models may be computed automatically, analyzed and compared. And in the left image, a partition-based partial residual plot reveals local deviations to the model. And on the right side, the deviation of two models, M1 and M2, are compared and displayed, which helps to identify differences and similarities between the model. In addition to analyzing raw features, interaction effects may be analyzed and transformations such as log and square are supported. Initial models may be refined by adding features, so guided by the display of their relation to the target. A user-defined partitioning is supported as well, and outliers may be analyzed with respect to their influence and can be removed. As we already assumed, temperature has the strongest effects. In the second use case, we consider epidemiology data with rich information potentially related to a target variable that represents a disease. Here, a flexible input of regression formula, including the variables, should be enabled as well as computation of the quality of fit for linear regression simultaneously. Epidemiologists have a strong background in statistics and are familiar with regression formula. Thus, a feature selection step to reduce the dimension to a manageable subset should be integrated. You should also consider previous knowledge, for example, for some diseases, women before and after menopause, for example, so around 52 years should be analyzed separately. In general, age and gender are confounders for most diseases. Here you can see some reasonable regression formula regarding epidemiological data. So first, compute all regression coefficients for any possible target, so which is indicated here by Z, depending on any pair of X and Y. Second, do the same but remove the influence of age, since we know that age is a confounder. Third, search for all pairs of features that may explain the occurrence of a cancer disease. And last but not least, search for all pairs of features that may explain Z, considering interactions between the two features. And to define the regression models, a text editor can be provided along with a list of possible regression operands and syntax checking. As basis, we used a breast-related dataset with 231 variables and 1,200 observations. Let's assume we want to identify 3 features that explain dense breast tissue, which could also be cancer tissue. For this purpose, we have to compute 231 to the power of 3 R squared values by involving 1,200 observations. This would need a long time, so we have to reduce the feature space. Based on a merit function and the correlation-based feature selection algorithm, the feature set is reduced based on entropy related to the target variable. With an appropriate threshold, the feature sets can be shrinked to 10 to 30 variables. However, remember, such feature selection is quite risky with respect to losing important information. To visualize the R-squared values, a color-coded matrix representation can be used. So the R-squared value for each regression is mapped to the saturation of color. In the left image, age is the target variable, and on the right side, all variables are considered as target variables, leading to this regression cube. The users may slice through the cube, for example with the mouse wheel, to get an overview of important features. Here a data set related to hepatic stenosis, so fatty liver, is analyzed using the heat map representation, and it comprises 199 features and is analyzed for men, women below 52 years and above 52 years. And you can see that some enzymes, uric acids and interleukin 6 levels are found as essential independent variables because due to their high values. Here you can see the heat map visualization of the R-squared values for our breast dataset. As a reminder, a dataset with 231 features possibly related to increased breast density was analyzed. The pregnancy status, the menstruation period, body fat portion, hip and waist circumference are essential to predict the increased breast density. And it was surprising that there is a strong correlation between kidney disorders. However, only 8 women are affected, thus the correlation is not significantly in this dataset. In general, you can say that users welcome fast target selection, simultaneous computation of many regression models, and flexibility of the output. However, the analysis is restricted to multiple linear regression models. and there are many known distinctively nonlinear relationships. So integrating regression is not a trivial task, and thus workflows are suggested to integrate regression. First, we have to select a target variable indicated here by targ, for example, a pathology such as fatty liver. Afterwards, for all pairs of attributes, so A1 and A2, check how they are related to the target variable. For this, use A1 as a primary variable and S2 as a moderator variable, so the partition can be low, middle, or high. With this, better splits are available as used in decision trees, but their computation is time-consuming and groups with few members may arise. Thus, if A1 has a strong linear correlation to the target variable, use a threshold, emphasizing it, and overlay fitting lines according to the moderator variable. If A1 has a low linear correlation to the target variable, then we can check for quadratic correlation to the target variable. So yeah, check for multiple regressions. So if A1 has a strong correlation, either linear or quadratic, search for attributes A2 as moderator variable only if A1 and A2 do not correlate. Keep in mind that for multiple regressions, the R-squared values have to be corrected. In case of strong quadratic correlation, we have to find quadratic curves. They capture the U-shaped or the J-shaped distribution. And keep in mind that all variables are centralized first, and the variance influence factor with a threshold of 5 is used to check for multicollinearity. Here you can see an example where age and body fat correlate to increased breast tissue density, so a feature with increased risk for breast cancer. For medium and high values of body fat, the correlation is relevant, indicated here by the green and blue lines. Also, the interaction of the triglycerides and body fat with increased breast density has a significant quadratic correlation. So the influence of body fat is lower the higher the triglyceride values. But the limitation of this framework here was or is that only numeric values can be considered. We can summarize that validation is essential to transform findings to trusted knowledge. So a regression model learned from some training data should be applied to some test data to study its performance. The overall data should be split into a training data set to learn the model, and a test data set to apply it, like other machine learning techniques, for example, any other classifier. In epidemiology, people start to apply their findings to an independent cohort. In conclusion, before regression is modeled, an understanding of the data and their reliability is important. So the distributions of each potential explanatory variable and the target should be checked. Appropriate features need to be selected, eventually transformed to yield normally distributed data, and partitioned to account for local effects. Partial plots enable validation of the influence of variables on the target and the model, and visual analytics solutions enable local model assessment, model comparison, and analyzing the potential influence of outliers. Here I listed some videos about the topics of this lecture where you find further information and details. So then thanks for your attention, and as usual you find all references used at the end of the slides, and yeah, see you next time when we talk about.